So we got our 3 classes of solvent. We've got. Oh, go ahead.
Is it because of solvation?
It is because of solvation, but I want something a little bit more specific than that. What's the ranking of your intermolecular forces in terms of strength?
The bottom is dispersion.
So the weakest is the London dispersion force, which is the only one that you'd have, right, if you have a nonpolar solvent. What's next? What are the other 2? There's London dispersion force.
There's dipole.
Dipole, dipole. That's for molecules that have a permanent molecular dipole, like, say, one of these polar electrolytic solvents. And
this one is ion dipole.
Okay, that's not an intermolecular force because it's an ion, not a molecule. But that'll be the next question: is where do ion dipole forces fit relative to these 3 intermolecular forces?
Are you looking for hydrogen bonding then?
I am. All right, that's the strongest of the 3 intermolecular forces, which we collectively call the van der Waals forces because we like to name things after people. But the key is that the ion dipole force is stronger than any of those intermolecular forces. Why is that true?
Full charge, or like 2 positive, 2 negative, depending on like what it is, but you have those full instead of partial charges.
It's Coulomb's law again, right? If you've got an ion, you've got a larger charge here than if you've just got a permanent dipole or hydrogen bonding, right? Even if you have a very polar bond, you only have a partial negative charge or a partial positive charge as opposed to a full charge. So your ion dipole forces are larger, right? Which means that the difference in force between the 2 ions that you're working with is going to be more significant than the difference in force between 2 neutral molecules that are interacting with any solvent less strongly. So the key to understanding the solvent effects, right, is to figure out where the ions are in the mechanism. And to figure out where the largest charge separation is. And the reason the solvents have a different effect on SN2 versus SN1 reactions is because the ions are in a different place. Right? So for the SN2 reaction, the starting material is an ion. Right? Because the nucleophile is often an anion. And the transition state has only partial charges. Because you've started to form a bond between the nucleophile, right? If I just take a generic nucleophile, has a partial negative charge on it, I've got my carbon, doesn't really matter what I have attached to it. I've got my leaving group here, also with a partial negative. So that transition state has a partial charge on the nucleophile. The starting material has a full charge on the nucleophile. So whichever solvent you're working with, it's going to have a bigger effect here than it's going to have there. Whereas for the SN1 reaction, the intermediate is the carbocation. And the starting material is neutral. Which has only partial charges. And since the transition state looks like the intermediate, and I'm only talking about step 1 here, because step 2 isn't the rate determining step, so we really only have to consider the first step, so the nucleophile is not really involved. Since the transition state looks like the intermediate, right, it's close to the intermediate on the reaction coordinate, so Hammond's postulate says it's going to look like the intermediate. that means that the solvent has a bigger effect at the intermediate and a bigger effect at the transition state. Okay. So for the SN2 reaction, the solvent has the bigger effect at the starting material. For the SN1 reaction, the solvent has the bigger effect at the transition state. Right, that's the second thing to know. And then the next thing to know is that protic solvents lower all energies, whereas polar aprotic solvents raise all energies. And that's because the protic solvents are actually solvating the anion really effectively with that strong ion dipole force. The polar aprotic solvents are basically unsolvating the anion. They're solvating the cation and leaving the anion alone, right? And it raises the energy of the anion if it's no longer associated with the cation, because you don't get that kind of ion pairing. Even in a solvent, if you have sodium fluoride, for example, right, some of those fluoride ions will be closely related with the sodium, so the sodium and fluoride will kind of be going through the solvent together as an ion pair. And what you do when you put a polar aprotic solvent in there is you surround the sodium with I just used dimethyl sulfoxide as the example. You surround the sodium with the negative end of the dimethyl sulfoxide dipole. Get this big solvent shell around it, right? And then fluoride's over here, no longer ion paired. Right? Sodium asks fluoride to go to the Presball with it, and then it gets to Presball and starts hanging out with all its friends and leaves fluoride without a date. Right? It pisses fluoride off, and it wants to start reacting. Right? If it's no longer ion paired, it increases reactivity. If it can't hang out with the sodium, it's going to go look for something to interact with, and that something is often the substrate, because it's a partial positive on this carbon, right? Fluoride is going to be attracted to that partial positive, and it can get close to that partial positive where it really can't get close to the sodium. Right? So those are the key things. Right? The key thing is to recognize where the anions are, or where the cations are. The ions are in the starting material for the SN2. The ions are at the intermediate, thus transition state for the SN1. Right? And protic solvents lower all the energies. Polar aprotic solvents raise all energies. What you're trying to do is you're trying to compare how much it lowers or raises the energy of the transition state versus how much it lowers or raises the energy of the starting material. If it lowers the energy of the transition state more than it lowers the energy of the starting material, you are going to have a smaller activation energy, which means the reaction is going to go faster. Right? If it raises the energy of the transition state by more than it raises the energy of the starting material, you're going to have the opposite effect. Right? So you're trying to draw the energy diagram with solvent and without solvent to see whether that activation energy should increase or decrease. Right? So the problem with this is you have to know the mechanism really soundly, really thoroughly, because the first step in answering a question about solvent effects is to draw the mechanism out so we can see what the structure of the transition state looks like relative to the structure of the starting material. Once you've done that, then you can argue about what the solvent is doing. So that'll be the quiz on Tuesday. It'll be a slightly longer quiz because solvent effects take a while, right? And if you didn't do very well on last Tuesday's quiz because you didn't know the mechanism very thoroughly, you've got to know that mechanism. The sections of the book you want to focus on, our book isn't very good. 7.4 is the section in Chapter 7 that talks about solvent effects. And I think it's page 235. It's in section 6.8, which was the section on nucleophile strength, but they kind of hide the solvent effect on the SN2 reaction in there. I think it's the bottom of page 235 and the top of page 236 is where you see a very brief discussion of the polar aprotic solvents increasing or the rate of the SN2 reaction.